Hi everyone, my name is Nicola Dreolin, and in this video I'm going to talk about the limitations of current ion mobility mass spectrometry instruments and future prospects for ion mobility. As usual, I start with a short list of topics that I will treat. I will first try to answer to the question, can we build a universal CCS database that can be applied regardless the technology type? And also, can we implement the CCS as an additional parameter in the identification criteria for regulatory methods? I will then provide a critical view of the current commercial IMS devices, laying out their main limitations. And I will finally, and I will finish with a personal view of the current state of the art and future prospect of ion mobility. Over the years, scientists and researchers have desperately attempted to find out if the CCS of an analyte obtained from a specific type of instrument is equivalent to the CCS obtained from another type of instrument from a different ion mobility technology. For example, comparing the CCS derived from traveling wave with the CCS derived from drift tube, trapped ion mobility, or differential mobility analyzer. And here I report the results from two works of Righetti et al., where they compared the CCS of a group of masked mycotoxins adducts obtained with the first generation synapse calibrated with the polydialanine and with the prototype Agilent 6560 drift tube. As we can see, percentage deviations are well above 2%, reaching over 11% for the acetate adduct of deoxynivalenol. It is possible that the different experimental setups influence the derived CCS, because from ion mobility experiments, K0 and CCS depend on the population distribution of ion structures sampled in the experiment. And therefore, if an ion undergoes isomerization or activation, deactivation before or during the IMS separation, the drift time will change, therefore the CCS will change. Sample preparation, ionization, and ion transfer conditions have an impact on the analyte conformation, and sometimes the low resolution of the current ion mobility technology does not allow to clearly distinguish between two different conformations or between different charges isomers, especially when we consider small molecules. Unfortunately, we don't have a combined uncertainty estimation of the CCS derived here to be able to compare precisely these values, so we assume a 2% to be conservative, but based on this example, we can clearly understand that the deviations are far too high to be able to consider the CCS as a technology-independent parameter. In a paper of 2018, these German researchers analyzed a total of 124 small molecules on a Waters Vion and also on an Agilent 6560 with the aim to understand if a common and therefore universal CCS database could be built and applied to both drift tube and traveling wave technologies. They monitored the protonated and associated adducts and found deviation below 1% for most substances. However, some compounds show deviations of up to 6.2%, which indicate that CCS databases cannot be absolutely used independently from the instrument type. Earlier in 2015, the Waters Research and Development Team presented a poster at IMS-mass, which focused on the assessment of precision and robustness of CCS values derived from traveling wave instruments, and made a direct comparison with drift tube CCS values available from the literature. Furthermore, they also modified in-house Synapt by replacing the traveling wave drift cell with an effective drift tube of 25.5 centimeter operating from 2 to 12 volts per centimeter. And this study involved the analysis of 177 molecules belonging to different chemical classes. Here at the top, we can see the absolute CCS values as a function of mass to charge for a group of analytes, and at the bottom we can see the percentage deviation of CCS of the same analytes, keeping the modified drift tube Synapt as a reference. And we can see that the difference between the two technologies is comparable to, or in some cases even lower than, the difference between drift tube values acquired by two different systems. Here we see a plot that shows CCS percentage deviations between the traveling wave technology, Vion and the Synapt, and the drift tube embedded in the Synapt system. In all cases, deviations are lower than 4% and in most cases below 2%. This plot represents the CCS percentage deviation uh, of the drift tube technology. Again, the modified drift tube Synapt is kept as a reference, and in red and green dots are the drift tube CCS from the literature. Here we can see that in some cases deviations extend to over 4%, even if we are considering the same technology, so the step field drift tube. This means that part of the deviation in CCS between traveling wave and drift tube is also present when we consider two different drift tube instruments, and therefore is not just technology dependent. So at present, we cannot really say that a common CCS database is employable regardless the technology type, although part of the reason is the still low reproducibility of CCS across different platforms, like in this case. Another issue is Another issue of currently available ion mobility mass spectrometry instrument is the low IMS resolving power. I will try to explain this, and to do so I will use a very recent paper from Kaufman where they presented the case study of veterinary drugs residues to find out if the use of CCS thresholds brings any additional benefits in regulatory methods for high throughput screening of contaminants and more generally small molecules in complex matrices. They used the Vion to screen a bovine liver extract for more than 100 veterinary drugs and metabolites, and process the raw data by applying the thresholds shown here against their homemade library. The results showed that when adding the CCS percentage deviation of plus and minus 2%, the number of false detects, which is the false negatives, decreased significantly. In other words, in a truly blank matrix, um, with the addition of the CCS filter to the workflow, the number of interfering peaks wrongly assigned as target analytes is decreased, and more precisely, the inclusion of the 2% delta CCS reduces the rate of false negatives by a factor of 4 or 5. The authors warn about the risk of encountering missing detects or false negatives, especially at very low concentration of analytes because of the presence of interfering isobaric peaks coming from the matrix that are not resolved in the ion mobility dimension. An example is shown in this heat map on the right, where a low level spiked matrix was analyzed, and we can see an intense peak with the same drift time as clenbuterol. But below the peak, there are actually two isobaric species, an ubiquitous plasticizer as phthalate and an unknown component coming from the matrix. These two components are not resolved by the mass and neither by their mobility. Therefore, if we know if the unknown compounds were to be a wet drug residue, it would have been missed by the peak detection algorithm because it would have been masked by the plasticizer. Thus, it would have been a false negative. With a higher IMS resolving power, the plasticizer and the unknown compound would potentially have been separated in the y-axis, even if they had the same molecular formula. It is safe to say that ion mobility enable ion high resolution mass spectrometry screens um, reduces the number of false positives, but it does not reduce the number of false negatives for compounds with an arrival time distribution very close to each other. Another consideration is about the presence of charge isomers, and charge isomers can be separated using using ion mobility and will produce a splitting arrival time distribution for an analyte. Therefore, the CCS of two protomers, for example, might change by over 2%. From one hand, this is great because we increase the peak capacity and we are able to detect two different species and potentially correlate the preferential formation of one charge isomer over another depending on the experimental conditions and use this information at our advantage. On the other hand, it can also be a drawback if we do not consider these isomers at all and we treat them as just one peak when building a library of CCS values. If the matrix affects uh, the charge or adduct, so basically the charge distribution or adduct coordination in a molecule compared to the same molecule dissolved in a pure organic solvent, which we use for building the library, then we can have a different arrival time distribution, which can lead to CCS deviation, which is not related to the lack of precision of the measurement, but or between solvent and matrix, but is rather due to the presence of fundamentally two or more different species, like in the case of enoxacin displayed here, where we can observe a different distribution of charge isomers when the analyte is present in the matrix compared to the solvent standard. This is clearly explained by this plot, where we can appreciate a negative bias of drift time when we consider a matrix extract. But when we exclude from the dataset the analytes suspected to produce protomers, we can see a drastic improvement with CCS deviations below 4% in most cases. A way to overcome this problem is to include in the library of CCS uh, basically the CCS of all charge isomers and assign them to the same analyte. In this way, we decrease the number of false negatives because we are considering all species that can form in a biological matrix. Of course, there will still be a number of potential false negatives, but this is true also for the mass to charge and retention time when taken alone. If we combine the delta CCS filter with the mass to charge and retention time filters, then we gain an additional effect that will reduce the number of false positive and also reducing the number of false negatives and really increase the detection and identification power. From my experience, when the system is well calibrated and when we can afford to work at 10 or 5 ppm mass to charge, delta CCS below 2%, and we add also a plus and minus 1 minute of retention time if we have the retention time data, of course. When I validate a library for a number of food matrices, I usually encounter no false negatives above the established LOQ. But of course, this will also depend on the matrix. If the sample, for example, contains an enormous peak, not eliminated by the sample preparation, and that perfectly coalesces with one of our analytes. It's an isomer with the same molecular formula or with a mass difference below 5 ppm. It has the same drift time, and maybe it also produces the same fragment. Then there is very little to blame ion mobility, and I would call this bad luck instead. But it is true that and Kaufman and co. pointed this out in their paper. If we had a higher ion mobility resolving power, let's say over 100, we would be able to increase the identification capability even further by avoiding missing detects, those false negatives, as well as reaching a better separation of charge isomers, and this is the case for both traveling wave and drift tube. In the scientific community, there is still reluctance regarding the addition of the CCS in their European regulation as half identification point for the screening of regulated compounds like veterinary drugs residues. And this is fundamentally due to three reasons. The low IMS resolving power, to the questionable orthogonality of CCS with the master charge, and to the fact that a common CCS database that is valid for traveling wave, drift tube, TIMS, and DMA is still not feasible if we want to keep the 2% CCS deviation as a maximum threshold, as we have seen before. And I'm going to spend just a few words on each of these points. But let me make one consideration first. Historically, ion mobility was born as a great tool in the analysis of large molecules like proteins, protein complexes, polymers, etc. In relatively recent years, we are trying to make it useful also for small molecule applications. And I have to say there are limitations in terms of mass to charge dependence and poor resolution of current commercial system, but IMS can bring a real advantage also in the small molecules identification, not only by the use of CCS, but also thanks to the reduction of background noise and interfering peaks in the low energy spectra and fragmentation spectra in the data independent acquisition. This said, the first point scientists make is that ion mobility is claimed to provide an orthogonal separation compared to the mass spectrometry, which means that the CCS and the mass to charge ratio should be two independent quantities. Well, this is not the case. The CCS and the mass over the mass to charge are not orthogonal. In fact, if we look again at the fundamental low field ion mobility equation, we notice that the CCS is derived from a number of parameters, including both the mass of the ion embedded into the reduced mobility mu, and also the charge of the ion. And this is not a recent discovery. Mason and co-workers already acknowledged the mass mobility correlation in 1975. Another thought is that for small ions, mu is the parameter that affects the mobility the most, whilst for large ions is the CCS the parameter that affects the most on the mobility K. And this is why ion mobility is particularly advantageous in the structural and conformational characterization of large molecules, as it can provide additional insights on the size and shape of an analyte. And the lack of orthogonality between the mass to charge and the CCS is not a surprise. Here we have a very nice picture showing the comparison of the mass to charge, the retention time, and the CCS taken 2 by 2 for selected triacylglyceride in milk. It is clear that there is a better correlation between CCS and mass to charge rather than the retention time, although it would be mistaken to think of retention time and mass to charge as perfectly orthogonal parameters either. In fact, the partition of an analyte between the mobile phase and the stationary phase is also driven at some extent, depending on the two phases, of course, by the polarity and also by the shape, size, and mass of the analyte. This said, we can recognize here on the top purple dots in the first plot. Those possess almost the same mass, but they are very well separated by the chromatography. A similar behavior can be recognized when looking at the second plot, where we have this series of dots, purple dots. And so basically, when looking at the second plot, where we have the dark purple, those dots here shown here on the top right, they have the same mass to charge, but are separated by the ion mobility. Not as dramatically as the retention time, but there is a separation. So even though CCS and mass to charge are not perfectly orthogonal, the use of the CCS in addition to the mass to charge and the retention time is certainly advantageous. The retention time is also not perfectly orthogonal to the mass to charge. However, the retention time contributes to the total identification score in confirmatory methods. And based purely on this first point, I don't see why the CCS uh, shouldn't be used in this criteria as well. In my opinion, the more pieces we have available, the easier will be to reconstruct the puzzle. And this is also shared by Masons and Revercombe in 1975 um, with their review on plasma chromatography. It is interesting to note that there is an analogy between ion mobility and chromatography. Both are separation techniques where the types of ion mobility, so drift tube, traveling wave, TIMS, DMA, FAMES, can be reconducted to the different types of chromatography, so liquid chromatography, gas chromatography, supercritic, fluid chromatography, ion chromatography, size exclusion chromatography, etc. The length of the mobility cell can be viewed as the length of the chromatographic column. In a traveling wave, for example, the potential and wave velocity can be the mobile phase flow rate, and the type of buffer gas can be viewed as the type of the mobile phase, leading to a CCS and a retention time. And if we think about it, there is even a stronger analogy with electrophoresis. In fact, Mason and Revencombe in 1975 referred to ion mobility as plasma chromatography or gaseous electrophoresis because the first devices operated close to atmospheric pressure and therefore it was like an electrophoresis in the gas phase. And CCS is a reproducible measurement, even more reproducible than the retention time, not only from lab to lab, but also from different points in time within the same laboratory and on the same instrument. Here I repropose a figure from from the same scientific article of Kaufman that I cited before, where he plotted the relative standard deviation of CCS and retention time during a period of 2 months for over 100 veterinary drugs. It is evident that the CCS is much more robust. The problem that all ion mobility systems suffer, I'm afraid, is the poor resolving power. Resolving power is defined by this formula, where X is the time in the time dispersing technologies and voltage for FAMES or DMA. So if we consider the arrival time distribution for drift tube ion mobility and traveling wave ion mobility, um, we can also refer to the CCS distribution, and where in this context the CCS, the delta CCS is the full width at half maximum of the CCS distribution. Delta CCS, not to be confused with the CCS percentage difference, which is defined by this formula. Despite instrument specifications published by vendors, the resolving power of commercial drift tube and traveling wave instruments very rarely exceeds the range 20 to 50. This is one of the major constriction of current systems. And this is an important point because it is limiting the precision of measurements, thus the precision of CCS-derived values. Even the most sophisticated peak picking algorithm will struggle with a broad peak, and the reproducibility of the measurement is affected. Here I report a figure from McLean Group, which shows the relation between the resolving power and the percentage difference in collision cross-section. In particular, it shows the required resolving power to separate two compounds in ion mobility with a known percentage difference in cross-section. But we can also read this graph the other way around. For example, if we had a resolving power of at least 100, as suggested by Kaufman, theoretically we would only be able to reach a baseline separation for ions with a CCS difference of at least 2.1%. Currently, we claim a CCS precision to be better than 2%, even though with instruments with a resolving power lower than 100. This means that we are able to distinguish two ions with a CCS difference of 2%, which are not well resolved in the IMS dimension. This could be one of the reasons why sometimes the peak picking algorithm fails in the detection of the apex of the peaks, and the derivation of the CCS leads to deviations higher than expected. Obviously, the higher the resolving power, the lower can be the CCS difference that we are able to detect. Ideally, we would like to have a technique which positions at the top right of this graph. That is a technique capable of resolving very well two ions that present a minimal difference in CCS. For the drift tube technology, increasing the resolving power can be achieved by building longer and longer drift tubes. So one could potentially build 1 kilometer drift tube for an outstanding separation. However, in addition to the band broadening due to the diffusion of the ions in a wider time frame in the time dispersive instrument, the problem is that the longer the drift tube, the higher should be the potential difference for keeping the working electric fields typical of drift tube instruments. And this has practical complications both from the electronics and safety standpoints. And this problem does not affect the traveling wave technology, where a modest wave voltage is applied between 8 boring electrodes, like 40 or 60 volts, which is moving at the wave velocity. This means that in traveling wave, we can have a longer device without the need for incredibly high potential difference between the beginning and the end of a drift cell. We are making improvements towards this direction, for example, with non-commercial structure for lossless ion manipulations, like this geometry shown here, capable of high resolving powers compared to the conventional linear traveling wave mobility cells. And this is an example of the separation of two peptides using a 90 centimeter drift tube and a 13-meter equivalent SLIM. Not only this, we don't have to forget the high-resolution ion cyclotron mobility spectrometry system developed by the Klemmer Group in 2009, which inspired water scientific fellows in a way that in 2019 the Cyclic IMS was finally launched, demonstrating remarkable separation capabilities. In the Cyclic IMS, the resolution has been proven to increase with the square root of the number of passes through the cyclic device, and we are now in a transition phase where the study of how to implement this in potentially routine analysis could bring additional benefits, and more applications are in development. The third limitation is that, as we have seen before, there are still issues in the creation of a common CCS database which could work for drift tube, traveling wave, DMA, and TIMS. And this could be the most challenging point to be treated. And for now, the only way we can make use of the CCS database is by building our own library for the compounds of interest. and validate over a certain period of time, possibly on multiple labs that use the same technology. If the precision under reproducibility condition of empirically derived CCS is high enough, which we know it is, we can use the database for screening analysis. This is also the rationale behind the use of product ion spectra, for example. The different collision chambers, geometries, as well as the non-standardized collision regimes prevent the exchange of spectra across different tandem quadrupoles or high-resolution platforms. Yet, we use product ion transitions in MRM methods and accurate mass of product ions in high-resolution mass spectrometry, and they are implemented in the regulation criteria, even if they can vary from lab to lab and of course between different technologies just as much as the CCS do. I would add another, let's say, additional limitation of current commercial ion mobility systems, that is, we still don't have reference materials with commonly agreed CCS values to be used universally for checking the bias of a measurements and for calibrating the secondary methods. Several sets of compounds and values currently are coexist, and this could be also one of the reasons for that explains the issues in building universal CCS databases. And this leads us to postulate some conclusions or outlooks for ion mobility. The common agreement on reference standards is certainly needed if you want to fully make use of the increased precision of ion mobility instruments. The problem is which compounds and how should we measure the accuracy of such values, given that the absolute true value is not known. The only strategy could be repeating the analysis of a selected group of analytes a number of times in as many labs as possible over a range of commercial and non-commercial drift tube instruments using the step field method under highly controlled conditions to lower the experimental uncertainty as much as possible, and thus derive the CCS using the fundamental low field equation and determine the reference CCS values as the mean from this proficiency test, which could be taken by convention as the true value. This is open to discussion as I'm not entirely sure it should be the way forward. I would rather like to find a way to improve the fundamental low field ion mobility equation, expand the model which can be used universally for any molecule, any ion, and lower the estimation uncertainty to be really negligible in all cases. Once we have a set of reference compounds, we should improve the calibration function for secondary methods in order to make them universally employable for any analyte, regardless the chemical class. We have seen in previous videos that significant steps forward have been made for the traveling wave, and we are in a phase where novel calibration equations will emerge and revolutionize the way we derive CCS on traveling wave ion mobility. In this way, we will really be able to compare the performance of different platforms and technologies in terms of both the precision and the accuracy. And it could even be that secondary methods properly calibrated could show better performance than primary methods. Another consequence of finding proper reference standards would be the possibility to create a common CCS database for all platforms, vendor neutral and applicable to any technology. Then something amazing would be the possibility to derive the traveling wave CCS and the trapped ion mobility CCS from first principle through a physical formula like the Mason-Champ equation. But this could be just an exercise in style for physicians and mathematicians if we are able to reach highly precise and accurate CCS values from an optimized calibration function. And finally, I want to conclude this video summarizing the key points that I have touched in this presentation. A, a universal database of CCS is still not achievable to all IMS platforms available today because deviation exceeds the 2%. Although this does not prevent us from building an in-house CCS database, validate it, and use it for screening and confirmatory analysis if we prove the performance are good enough, which means if we can achieve good precision. And we and the use of the CCS is with no doubt advantageous if implemented in the identification workflow with the retention time and accurate mass of precursor and fragment ions, as it helps decrease the number of false negatives and false positives. Lastly, research is definitely ongoing and significant progress is expected very soon. For example, in the improvement of the calibration equation for the traveling wave, or even a first principle equation for the direct CCS derivation for the traveling wave and TIMS. Improvement of the resolving power of commercial systems are also expected. The recent launches are quite promising in this respect, and this will lead to higher precision measurements. And finally, I believe that the definition of universally accepted reference standards will be undertaken very soon. With this, I want to thank you for watching and remind you that you can find all the references at the bottom left of each slide. I hope this short series of videos on IMS and CCS has been useful, and like always, you can comment, propose your ideas and suggestions. And you can find me on LinkedIn and ResearchGate. Ciao.